What vitamin and mineral cofactors are needed to synthesize and recycle BH4, also known as tetrahydrobiopterin, which is a cofactor for a number of enzymes that make it essential for the synthesis of dopamine, norepinephrine, epinephrine, and serotonin, as well as preventing the disorder phenylketonuria and having possible roles in many conditions of health and disease, including Alzheimer's, Parkinson's, and depression.
This is a clip from a live Q&A session open to CMJ Masterpass members. In addition to this episode, you can access lots of other free samples from these sessions at the first link in the description.
The first runner-up comes from CMAS. You can, start over. The first runner-up comes from CMAS. I summarize his question as what cofactors are needed to synthesize and recycle BH4 or tetrahydrobiopterin. CMAS's full question goes like this. I'm resubmitting my question from last Q&A as suggested by Chris. What role does folate and methylation play in synthesizing and recycling BH4? What cofactors are required for recycling reactions with the enzymes DHFR and QDPR? Originally, I was mostly interested in how folate and methylation affect neurotransmitter and nitric oxide synthesis, and then I figured it's probably mostly through BH4. However, then I remembered the studies where SAMe was successfully used for depression, which is interesting because SAMe seems to mostly be a cofactor for neurotransmitter breakdown. I wonder if there is some kind of feedback mechanism between COMT and amino acid hydroxylases which increases turnover, or some other mechanism. It seems like it's not really clear, at least from the studies I've seen. So I'll go back to my summary of the question, which is what cofactors are needed to synthesize and recycle BH4? So the first thing that I would like to go to, I'm going to share my screen, and I'm going to show you the structure of folate from the folate chapter of Modern Nutrition, Health, and Disease. So ignore the two structures below and look at the one at the top. And what you'll see here is that folate has a pterin ring and then a para-aminobenzoic acid moiety. Moiety is just a part of a molecule. And then has at least one glutamate residue. A glutamate residue is the amino acid after it's bound to something else in a peptide bond. You call it a residue of an amino acid because it loses its acidity once it does this. It's no longer an acid. It's an amino acid residue. And so this is folic acid. Folate will have the nitrogen ring here fully reduced, meaning hydrogen ions and electrons are added to it. And it will also have some number of polyglutamate side chains over here. So this glutamate residue can just be repeated many times over. What I want to draw your attention to is BH4 and BH2 are tetrahydrobiopterin and dihydrobiopterin. And folic acid is successively reduced to dihydrofolate and tetrahydrofolate. So the similarity here is that the structure of BH4 and BH2 essentially is the pterin ring of folate. It essentially is the pterin ring of folate without the PABA and the glutamate bound to it. And what gets reduced to reduce folic acid to dihydrofolate and tetrahydrofolate is the reduction of this ring. So the double bonds go away and the nitrogens get hydrogens added to them. All that is, and what you don't see in these structures, they draw it so that the points between lines, the angles, are carbons, and you infer that there are up to four. You infer that every carbon has 4 binding sites, and whatever is not explained in the picture is bound to a hydrogen. So, for example, this carbon right here has 1, 2, 3, 4 binding sites filled because of this double bond and these two carbons, and so it does not have any carbons. It does not have any hydrogens added to it. Whereas this carbon has 1, 2, 3 bonds, and so you can infer that this has a hydrogen there. So you won't always see it in the structures, but what's happening is that you have a hydrogen ion and an electron added to 2 sites to generate dihydrofolate from this, and then added again to 2 sites to make tetrahydrofolate from this, all using the enzyme dihydrofolate reductase, or DHFR. And if you have BH2, which is dihydrobiopterin, you essentially have this pterin ring like it would look in dihydrofolate, but without the PABA and without the glutamate. And you will add 2 hydrogens and 2 electrons to this nitrogen ring. And so, therefore, folate and BH2 are alternative substrates for dihydrofolate reductase. And that enzyme can metabolize one or the other by doing the exact same thing to it. Now, part of the question was, what role does folate or methylation play in the recycling of BH2 to BH4 with DHFR, dihydrofolate reductase? I mean, obviously no role, because they're alternative substrates. There's no role of folate in the reduction. That's what you would predict if you just look at the structure, is absolutely nothing. But with that said, there's a lot more to the question, which is, what are all the cofactors to the synthesis and recycling of BH4? So let's go through it step by step. First of all, why do we care? So BH4, or tetrahydrobiopterin, is a cofactor for the enzymes phenylalanine hydroxylase, which converts phenylalanine to tyrosine, tyrosine hydroxylase, which converts tyrosine to L-dopa, and tryptophan hydroxylase, which converts tryptophan to serotonin. These 3 are grouped together as being called amino acid hydroxylases. But then there also is alkyl glycerol monoxygenase, which plays a role in lipid metabolism, and nitric oxide synthase, which uses arginine to synthesize nitric oxide. And collectively, BH4 is needed for the synthesis of dopamine, norepinephrine, epinephrine, and serotonin as neurotransmitters. And a genetic defect in its synthesis is one means of developing the disorder phenylketonuria, because although the main classical phenylketonuria is a defect in the amino acid hydroxylase that metabolizes phenylalanine itself, a defect in BH4 will compromise the cofactor supply for that enzyme, indirectly compromise the enzyme, and lead to the non-classical form of phenylketonuria, phenylketonuria, which is named after the appearance of abnormal metabolites and phenylalanine in the urine, but which is a neurological disorder that's driven by high levels of phenylalanine outcompeting other amino acids into the brain, and then on top of that, outcompeting other amino acids for their metabolizing, thus lowering the neurotransmitters derived from other amino acids, and at the same time having excitotoxic effects itself, causing a broad range of neurological dysfunction. And BH4 has additionally been implicated in common disorders. So possibly it's limiting, BH4 being limiting has been implicated as having a possible role in Alzheimer's, Parkinson's, and depression. Now, in these enzymes, BH4 sometimes acts as a redox cofactor, which makes it lose electrons to become a quinoid form of BH2. But sometimes it does not become oxidized during the enzymatic reaction. For example, in nitric oxide synthase, it does not become oxidized as part of the reaction, but it can become oxidized incidental to the reaction. So especially when nitric oxide synthase is involved in the oxidative burst in immune cells, you have a copious oxidants being produced, which creates a very high risk of the BH4 undergoing incidental oxidation, in which case you again wind up with BH2 that needs to be recycled to BH4. When you synthesize BH4 de novo, meaning newly, which is sort of it's not ex nihilo, from nothing, but it is newly, meaning you're not just recycling BH2. And by the way, they call the recycling of BH2 to BH4 the salvage pathway, which I find really weird because usually the salvage pathway elsewhere refers to like significantly more degradation than just having something oxidized. But it is what it is. In the literature, they call BH2 recycling the salvage pathway. So the de novo pathway is the synthesis from precursors, and it uses 2 or 3 enzymes. The first enzyme, which is always used, is GTP cyclohydrolase 1. The second enzyme, which is always used, is 6-pyruvoyl tetrahydrobiopterin synthase. And in addition, sometimes sepiapterin reductase is used. What happens is that the second enzyme is capable of carrying out multiple reductions, and if the final reduction is carried out, it leads directly to the synthesis of BH4, but there is some amount of intermediate that escapes that second enzyme as sepiapterin, which requires sepiapterin reductase to be converted to BH2, at which point dihydrofolate reductase, a fourth enzyme, will essentially become the fourth enzyme in the de novo synthesis, because what happens is the recycling part becomes active, right? So if you go through GTP cyclohydrolase 1 and the full set of reactions of 6-pyruvoyl tetrahydrobiopterin synthase, you'll get BH4 without the BH2 intermediate. But if you have sepiapterin spill out and be metabolized by sepiapterin reductase as a third enzyme in synthesis, essentially the so-called salvage pathway takes over as the fourth step in the de novo synthesis, converting that BH2 to BH4. Now, the first enzyme, GTP cyclohydrolase 1, requires zinc as an essential cofactor. In rats, it has been shown that magnesium activates the enzyme. That's probably true in humans if it's true in rats. Generally, not always, but generally mammalian enzymes share properties. You can also infer that GTP is going to be active as a magnesium chelate. So if you don't have enough magnesium in the medium, it might compromise the reaction that way anyway. The second enzyme, which is 6-pyruvoyl tetrahydrobiopterin synthase, requires NADPH, which is derived from niacin, vitamin B3, and it also requires magnesium. The third enzyme, sepiapterin reductase, also requires NADPH, again, a form of niacin or vitamin B3. So basically, the cofactors for the de novo synthesis of BH4, well, if we include sepiapterin reductase, we have to include DHFR. And DHFR requires NADPH and is stimulated by potassium. So you could say that the essential core of de novo synthesis requires zinc, magnesium, and niacin. Of course, the NADPH, you also have to realize, is ultimately dependent on other pathways, such as the pentose phosphate pathway producing NADPH from NADP+. But putting that aside, directly what's needed is zinc, niacin, and magnesium. And if you extend de novo synthesis to include sepiapterin reductase and DHFR, then the full cofactors for synthesis are zinc, magnesium, potassium, niacin, that's it. Because the potassium is coming in from DHFR. So zinc, magnesium, niacin, and potassium are the full cofactors needed for de novo synthesis, including the extended reaction sequence. And then on top of that, for recycling through DHFR, and it's just NADPH and potassium. Now, when the amino acid hydroxylases, those three first enzymes I mentioned use BH4, they generate a quinoid BH2 intermediate that cannot be directly metabolized by DHFR. It can be converted to BH4 using dihydropteridine reductase, which is sometimes abbreviated DHPR, or is sometimes called quinoid dihydropteridine reductase, in which case it is abbreviated QDPR. And this requires niacin in the form of NADP+. So it's the opposite. And so you can imagine, even without the pentose phosphate pathway, if you require NADP+ for regenerating BH4 from the quinoid form of BH2 released by the amino acid hydroxylases, then you have some reactions that are oxidizing NADPH and producing NADP+, some reactions that are using NADP+ to oxidize the quinoid form, in which case it should be regenerating NADPH, and you might have some cycling there that doesn't directly rely on the pentose phosphate pathway. Now, if this reaction does not occur, the quinoid form of BH2 will spontaneously convert into BH2 eventually, and then be recycled by DHFR, in which case you are back to using NADPH and potassium as your cofactors. Ultimately, this does not depend on folate in any way, and it does not depend on methylation in any way. But that said, let me just emphasize for you. So I'm going to show you two things. One, I want to recap from the beginning. Remember, the pterin ring of folate is essentially BH2/BH4. So if dihydrofolate gets metabolized by DHFR to reduce this specific nitrogen ring of dihydrofolate, and if BH2, which is basically this without the PABA and glutamate, has to get this homologous nitrogen ring here reduced by DHFR, then obviously from the structure, NADPH is reducing either of them, and they will both have to occupy the active site in the same place as alternatives. And the folate has no role in this because it's not in the enzyme when that's happening. But let me just show you what the enzymological models have shown for the sites occupied in this enzyme. So this paper is functional role for tyrosine 31 in the catalytic cycle of chicken dihydrofolate reductase. This is the only paper I was able to find to show a model of where these occupy. On the left, you have folate here, and on the right, you have biopterin in purple in each case. And then the niacin derivative, the NADPH, is, I believe, is the other color. Oh no, they're emitting the NADPH. Oh, and the red color is the phenylalanine 31 residue. So I'm not trying to highlight anything about that residue. So I want you to focus on the purple. So this molecule is bigger because it's folate, and it not only has the pteridine ring, it also has PABA and glutamate extending from it. On the right, you have BH4, which is the pteridine ring, which is basically the pterin ring of folate without the PABA and the glutamate. Then it's occupying this exact same corner in the enzyme. So there's no room in here for folate to come in and do anything. So the answer is that this has nothing whatsoever to do with folate or methylation in any direct way. Granted, biological complexity is like an onion. You peel off one layer, you find another layer. So I'm not saying that if you keep peeling back the layers, you're not going to find any interaction with folate or methylation. Of course you will, because everything is interrelated in biology. But in terms of what's directly taking place, nothing at all to do with folate. Now, the sort of second part of your question was about SAMe. It's useful for depression, which is interesting because SAMe seems to mostly be a cofactor for neurotransmitter breakdown. I wouldn't necessarily say that. SAMe is a cofactor for the synthesis of several neurotransmitters. It's involved in dopamine breakdown, but also dopamine synthesis. It is involved in norepinephrine production and so on. So I don't really agree with that. I think the role of SAMe is quite complex and conflicting across the totality of neurotransmitters. And I think SAMe is generally a pro dopamine molecule, which I think is antidepressant. Um, Actually, it's a pro dopamine, pro norepinephrine molecule, which are both antidepressant. But it is very, very highly specifically a pro dopamine compound because not only is it involved in the synthesis of dopamine, but it is also involved in decreasing the baseline tone of dopamine, which makes the phasic pulses of dopamine look bigger to the brain, which allows the brain to be more mentally flexible and more motivated and interested in new things. And I think that particular aspect of dopamine is very antidepressant. But in any case, Simas, I hope this helped answer your question. Thanks for it.
This is a clip from a live Q&A session open to CMJ Masterpass members. In addition to this episode, you can access lots of other free samples from these sessions at the first link in the description. If you want to become a Masterpass member so that you can participate in the next live Q&A, or so that you can have access to the complete recording and transcript of each Q&A session, you can join at chrismasterjohnphd.com/masterpass. You can save 10% off the subscription price for as long as you remain a member by signing up at chrismasterjohnphd.substack.com/Q&A. That's Q&A spelled out as Qanda. These links are in the description.